This is problem number 20 from section 3.2. The problem is talking about a harmonic oscillator. Here is the general equation for the harmonic oscillator, where m is mass, b is the damping coefficient, and k is the spring constant. We're given m is 1, b is 5, k is 4, and so here is our second order linear differential equation that describes this damped harmonic oscillator. In its system form, it looks like this, and this is the form that we're going to work with, and the coefficient matrix is given by this, okay? And so we can write this system as a times y, where y of t is made up of the position little y and its velocity little v. So in the next page I'm going to find the eigenvectors and eigenvalues, and we'll move from there. So now on this slide I've already computed our eigenvectors, our eigenvalues and eigenvectors. Again, this is our characteristic equation, which leads to our characteristic polynomial. And when I factor the polynomial, I find two eigenvalues, two distinct real eigenvalues, lambda 1 equals to -1 and lambda 2 equals to -4. Then I go through the procedure of finding the eigenvectors. That's nothing more than taking the matrix A and saying that A times YV has to equal -1 times YV. So here's -1 times Y, -1 times V. Set this up. These two equations will be redundant. The first one's already clear that V is the negative of Y. The second one, after you bring the minus V to this side, turns into the same equation. And so V always has to be the negative of Y. So if I pick Y to be 1, V is a -1. That's an eigenvector. In the second case, when lambda 2, the second eigenvalue is -4, we set up the same equations. Here's A times the coefficient matrix A times Vy has to equal -4 times YV. And again, we get two, this is the same system, two redundant equations that V will always be -4 times Y. Choose the Y to be a 1, and the V then is a -4. Those are two of the many possible eigenvectors, but they're the simplest ones that we can find. Okay, next we find solutions. The way we build solutions, given an eigenvalue of -1 and its corresponding eigenvector of 1 - 1, this is the standard form for a solution of a linear system. E to the eigenvalue times t times the corresponding eigenvector. And note that at time 0, its initial position is at 1 - 1. The second solution is e to the eigenvalue times t, so e to the -4t times the corresponding eigenvector 1 - 4. At time 0, it's at 1 - 4, and I want you to note that these two solutions are linearly independent. These two eigenvectors are linearly independent, and so these solutions can be used to build the general solution if we need to. In part C, it says to graph these solutions in the YV plane. These are both straight line solutions. I'm going to make a rough attempt at doing this. Here's the y-axis. This represents position, right? That's position of the mass. Here's the v-axis. That's the velocity of the mass. This isn't so easy to do without graph paper, but roughly the the y1 starts, so this is going to be a little tricky, but starts, I'll do it in red, starts right here at time 0 at 1, at the point 1 minus 1, over 1, down 1. This means it has an initial displacement. This one means it has an initial displacement of 1. This minus 1 means it has an initial velocity moving in the negative direction, and its velocity is 1. So moving back up, moving downward, moving in the negative direction. Still, this is a heavily damped system. All solutions lie on the line 1 minus 1, and as t increases, this gets smaller and smaller, and so the solution is just this little straight line that starts here and moves to the origin but never reaches it. Similarly, the solution for y2, the graph of y2, starts at 1 minus 4. 1, 2, 3, 4. Starts roughly here, and it is a straight line. As time changes, we're always staying on the straight line, and it's moving towards 0, 0. And that's part C. So I have quickly drawn, simply graphed the two components of y1. Here's its x of t component, here its y of t component. They are symmetric, but they live on different sides of the plane of the time axis. Here's a graph of the two components of y2. Here's its x of t graph. It starts at 1 e to the minus 4t after that, and this starts at minus 4. The y component starts at minus 4 and then decays at the rate of e to the minus 4t. Not the most accurate drawings, but roughly that's right. In the last part, they ask you to talk about the interpretation. The fact that y1 at time 0 has a value of 1 minus 1 means that it has a positive displacement of 1 unit. It has a negative velocity of 1, and so if this spot is the rest position where the mass was originally before it was disturbed, the positive displacement of 1 means we pull it down 1 unit. The negative velocity, so we're pulling it into the positive direction 1 unit. And the negative velocity would mean when we release it, we're not just letting go, we're actually pushing up with an initial velocity of minus 1, so we're pushing it towards the rest position with a velocity of minus 1. What we see in the result, however, is because this is heavily damped, nothing, so if we come up here and look at the solution, all that happens is the position slowly returns to the rest position at an exponential rate. It doesn't pass it because it's heavily damped. I'm not going to do the very last part, talking about the interpretation here, but it's very similar. That's it. Thanks.